Amazing. Okay, well, I'll hand over to you, Sam, then.
Great. Yeah, thanks, Andy. Thanks, everyone. So today I'm presenting on some pretty preliminary stuff. It's relatively applied by my standards, but has a lot of nice sort of modeling and algorithmic aspects to talk about. And I don't necessarily expect to say everything I have on the slides here. I'd rather make sure people understand what the model and the problem are, and then the algorithms are sort of details we can talk about more later. I think they're interesting, but I'd rather have the problem be well understood. So this is joint work with Lorenzo, who's also on the grant, and then Sam Duffield, who I sort of worked with a bit during my PhD in Cambridge, who's just finished his PhD. Okay, so I'll basically start with some warm-up hypotheticals of situations where you need to make certain decisions. So let me see if I can click through. Right, so before we get to statistics or probabilistic modeling, just talking about some scenarios you might be in. So one is you're arranging a board game night with a bunch of friends, and you're playing a game that some of you have played before and some of you haven't, but you all kind of know each other a little bit. And there's some sort of teams involved, it's not everyone against one another. So as the person organizing the board game night, if you have some knowledge about the people you're playing with, you probably want to divide up the team so that things are relatively fair, such that each team has some people who understand the game, and such that, when you play the game, it's relatively competitive, but also fun for everyone who's involved. There's these things to trade off. So at a slightly larger scale, you can be thinking of sort of competitive sports tournaments where you have, just think of singles things, so 1v1 games in different formats like chess and tennis, where again, coming into the tournament, you have some knowledge of the games people have been playing beforehand and what to expect from them in terms of performance. And so you need to set up a seeding for the tournament where you need to organize the schedule. Again, to make things fair, to sort of guarantee that the most interesting games happen, and to some extent that the right people progress to the right extent. Although this is sort of, it's not exactly you're doing experimental design to come up with the best player. Somehow there's more to sport than that. But the design of the games that you set up, you want to inform in a certain way. Right, and then increasing scale to another level, you might think about online gaming. So, pick your favorite online game from your generation. For some people, that's Dota or Counter-Strike, or these days, League of Legends, where, you have an online gaming community made up of thousands upon thousands of people at the very least, and possibly even orders of magnitude more than that, playing games constantly in time in big teams. And again, you have very high frequency data coming through about how good these people are at the game through the results that you see. And you need to be able to match up teams randomly appropriately in some settings, again, for the same reasoning as before. So in each case, you're sort of, you are, here today, you imagine yourself as the administrator of these things, the person organizing the tournament or, running the game. And so what you have to do is actually make decisions and take actions, right? And so the perspective I want to take today, which sort of, it's always there in the background statistically, but I think this is a setting where you really want to think what I'm doing is I'm trying to use data to inform predictions so that I can make good decisions. And, everything is instrumental to that end. If you're doing more and more accurate statistical inference, but it's actually not panning out well on the decision side, then there's more work to be done. Okay, and so today, just, it's terminology, but anytime I'm talking about this, competition, I will call it a sport. And, depending on where you stand on the question of whether things like chess and board games count as sports, for the purposes of today's talk, I will call them sports because I don't want to have to keep qualifying everything along the way. So along the same lines, a match will refer to a sort of 1v1 competition between two players. Again, sort of sweeping under the rug the fact that you might have teams involved, or in tennis, you have different sets and so on. Today, we'll focus on the setting where for each match, you observe a win-lose outcome. Again, this sweeps certain applications under the rug, but you'll sort of see as we go, some of these things you can adjust to pretty gracefully. Some of them require rethinking the modeling a little bit more, but it's certainly simplest to think of this paired comparison scenario. Right, so that's the soft introduction. And now we can start talking about how we might actually model this mathematically and probabilistically towards doing some statistics, say. So the most common paradigm for doing these things, which I'm aware of, is your observations. They depend on the players who are involved in some way, and you want to model them as having some unobserved skill level in abstract, which will be a latent variable. And today we'll think of these as being univariate, although again, there's a great deal of room for generalizing this, and you can think of many scenarios where you can be a lot cleverer. So you have these unobserved skill levels, and you observe them indirectly through the outcome of a match, right? So, two people are playing chess against one another. Secretly, player 1 has a skill level of 12, and player 2 has a skill level of 33. And when you play the game, you'll observe the outcome, and that will make you think, oh, this guy's very talented, And so in these applications I was talking about, particularly these high frequency online gaming type ones, it's important to model the dependence of these skill levels in time. Right? You're assuming there's some evolution of the skill level, because otherwise you can kind of do static inference. And in some cases that's appropriate, but today we'll be thinking actually this temporal aspect is relevant. And so you will see that it's kind of natural to model these things as a state-space model, where the unobserved variables are these skill levels. Now, a standing assumption we'll make, and which is made in the literature in general, is that the dynamics with which the skill of a given player evolves are independent across players. Okay, so one usually doesn't model an effect of these two players play and then they learn from that and they get better as a result of it. It's always kind of there are natural fluctuations in a person's skill level over time, and we assume those to be uncorrelated. Again, in the examples I mentioned, the dynamics will also be kind of IID across players, but to some extent that's not too hard to modify. Okay, this is annoyingly put a space mark here, but a key feature is that this is not going to be sort of evenly spaced data, right? The matches occur inhomogeneously in time. Sometimes you will observe multiple data points at a single time instance. Other times you'll wait, a while because it's been the summer break and everyone stopped playing, and blah, blah, blah. So you can't sort of assume things to be homogeneous, and this will affect some of the computational aspects. Okay, and then crucially for sort of the difficulty of the model is any match involves order 1 players. In tennis and chess, it's particularly pointed because you couldn't really have a match with just one player, and so 2 is sort of the least you can do to get a bit of comparison information. Right, so we can now begin to talk about, we can now begin to talk about some actual models that people consider for this, again, building up sort of through time and complexity. And I'll try to annotate things with where they actually arose historically, because I find it interesting. Okay. Oh, no, sorry, one thing in between. So what do we actually want to do with these observations? So what we almost always want to do is some kind of filtering, right? We want to have online estimates of the skills of each players, because that is most relevant to decision making somehow. Because having an estimate of the skills of each player is sufficient for predicting how they will perform, and that is what will inform our decisions. And I'm back. Okay, in many situations, we'll also be interested in parameter estimation for the different parameters of the dynamics of the process and the observation model. And this will be useful for calibrating the model in different ways. So we'll see some examples of how that can be useful going forward. And what tends to be the case in many of these examples is that to do efficient parameter estimation, you will need to do some sort of smoothing of the player's skills over time. So for things like the EM algorithm and gradient descent, the relevant quantities for moving your parameter estimates involve expectations under the smoothing distribution. So the distribution of the player's skills over the past in time condition on everything you've seen. Yeah, and so it's, sometimes it's also of intrinsic interest. So, in some applications, you will actually really be interested in how do we think this player's skill developed over time. So, when I was learning about this area for the first time, my collaborator Sam, he had recently been looking at an application based on the US Open, which had just happened. And if you remember, the winner of the women's final was Emma Raducanu, who prior to this tournament was ranked, 300 or 400th in the world, something sort of relatively low. And so her win was kind of a big surprise. And so it's an interesting example where you can kind of do the filtering and smoothing, and you can see, you know, on the filtering path, you're gradually drifting towards thinking she's a very good player. And then, of course, when you do the smoothing, you sort of see like, oh, in the past, we should have seen this coming to some extent. Or even, you know, a week ago, we thought she might have been a better player. But yeah, so in what we talk about, I think we will largely focus on smoothing as a component of doing parameter estimation, but there are examples where you care about the smoothing for its own purpose, even just historically. Right. So some existing approaches. I mean, you can imagine there's many, many ways of doing things, but I'll sort of try to give a bird's eye view of, you know, the development of as I understand it. So perhaps the most well-known is something called the ELO rating system, which was developed for chess players, essentially, I think in the 60s or so. But it's very long-standing and extremely widely used. It is not explicitly based on a probabilistic model, and actually the derivations of the model are somewhat hidden. I think it's sort of implied that ELO himself, you know, he set up a model, fit it to data, and then kind of hid that from the world and said, here's the rule. So let me just see if I can write out what it looks like. So if I write xi for the skill of player I, right? If I have a game where player I and player J face off against one another, and I observe the outcome Y, which is equal to 1 if I wins, and 0 if J wins, then what happens is you replace your estimate of xi with xi plus k times y minus your probability of xi beating xj, right? So if player I wins, your guess of their skill goes up, and k here is just a constant factor. And similarly, you would send xj the other way, basically. And so, as I said, there's not an explicit probability model here. It sort of, you know, looks vaguely like a number of filtering recursions. Like it looks very closely like the Kalman filter. It looks a little bit just like stochastic approximation. But again, you see that you'll be stationary if kind of this matches up with the expected value of the win, then you're properly calibrated, right? And so that's ELO, and ELO is kind of, you know, extremely widely used, even beyond chess. There's many, many sports where it's, you know, the tool of choice somehow. It's at one end of the spectrum in the sense that it is so easy to understand that you don't really need to have a background to make sense of it. You sort of understand, oh yeah, if you win, you go up. If you win and you really weren't expected to, you go up even more, okay? From the statistical point of view, it's sort of unsatisfying, or at least it sort of draws you in to want to add more to it, right? There's the basic thing you can say is this parameter k. You know, in chess, it is chosen to be a specific constant, like 16 or 32 or something like this. And what is observed is that if you try to do ELO for different sports, the sort of appropriate value of k for calibrating skill estimates changes. So to some extent, you can say, okay, well, how should I actually calibrate this parameter? And so from the point of view of, you know, various statistical professions, it makes sense to sort of fit a probability model to it and then use some approach based on that. Okay, just click through. Okay, so another thing which is sort of a more classical statistical model is what's called a Bradley-Terry model. And then there is sort of what's called the dynamic Bradley-Terry model, which is somehow the state space version of this. And again, it's just this intuition I told you before. If you have a latent variable that represents your skill, and then you observe the outcome through a sort of logistic type observation. So, you know, the winner is a Bernoulli, and the probability of player I winning is a logit applied to skill of player I minus skill of player J, basically. And so because this is, you know, it's been around for a while, and it's sort of very orthodox in a statistical sense, most of what I've seen of it seems to focus on doing things in the static setting. So the model is sort of dynamic, but you say, I observe data in a batch format, and then I do inference on it in kind of an offline way. But in principle, there's no reason you couldn't also do it online. Right, so in, I think, the early 90s, there was a refinement of ELO called Glicko, which is invented by a man called Mark Glickman, who was a biostatistician, I think, at Harvard, but also the head of one of the chess foundations in the US somehow. And so if you read the paper where he proposes this, it's sort of framed as, a generic statistical method for inference based on paired comparisons or something like this, or the title at least has that flavor to it. And of course, when you dig into it, it's really specifically about chess and building a system for inference in chess. But again, if you look at the sort of model he has there, it is sort of structurally the same as the Bradley-Terry model. So you have, your latent skills are Gaussian in law, and they just evolve under sort of a Brownian random walk in time. There's reasons why, that should give you pause and reasons why it's a bit strange, but I'll comment on those later. Anyway, so Glicko you can sort of think of as a dynamic Bradley-Terry model where you approximate the inference step based on more or less the extended Kalman filter, just a sort of linearization and then Kalman filter step. And then true skill is more recent. I think the original incarnation is from around 2000, and then over the next 10 years or so, they developed it more. This was developed by Microsoft for the Xbox, basically. So for things like rating players on Halo and other online shooters, this is what true skill was developed for. And again, because it's adapted to this high frequency setting, the algorithms change a little bit as well. So structurally, it's again pretty much a dynamic Bradley-Terry model. They changed it to probit observations rather than logistic. This is kind of to make things nice with respect to the Gaussian character of the problem. And then the updates are done through, there are many ways of calling it. You could call it moment matching or assumed density filtering or expectation propagation. There's sort of slight differences between these things. But the idea is, again, you maintain an approximate posterior for each player at each time, which is independent of one another and Gaussian, okay? And so that's the filtering step. And what's sort of common to all these models is if you want to do smoothing, you just kind of pretend you had a linear Gaussian model from the start and run a Kalman smoother backwards in time. Okay, and now to just talk about some common threads of these things. So in all these examples, the skills are modeled latently as being Gaussian with independent Brownian motion dynamics, okay? And so I found this strange at first because you'll sort of notice, okay, in this setting, the player's skills will sort of fluctuate and diverge even over time, which I found strange at first. But then if you kind of dig into the chess literature and so on, they say it's actually not so strange because over time people learn new things, and the best chess player now would trounce the best one from 20 years ago or so on. I think it's kind of a bit of a, I haven't come down on one side yet, but that's something we're interested in assessing a bit more. But it's, you should at least look at it and say it's not completely obvious that that's sensible. Yeah, throughout, with the sort of vague exception of the dynamic Bradley-Terry, is that you're trying to do approximate inference so that you keep everything involved independent, Gaussian, and fast. Yeah, and throughout you try to make sure that the scaling with time is always O of t. Somehow you couldn't get it any better than that, and this is sort of the cheapest thing, at least in the filtering setting, it makes sense. From what I've seen, there seems to be a limited focus on online parameter learning in this setting, but I suspect that I'm missing something or reading the wrong parts of the literature, because given the online nature of a lot of these things, it seems like a strange thing to overlook. So I'm mostly putting that on myself, but I'd like to see more about it. Okay, so one of the things we were interested in this setting was the modeling aspect of it, and in particular to sort of say, is it really sufficient to model everything with Gaussians? So I think what people observe is that doing these approximate filtering steps to go from Gaussian to Gaussian doesn't induce so much of a bias. So the question I'm really interested in is actually from the modeling side of these filtering distributions, you're getting good representations of the filtering, the predictive distributions you want to make. So yeah, it's very convenient to work with Gaussians throughout, but it's a bit limiting. There's certain things where if you want to change aspects of the dynamics, it's not completely trivial. Yeah, and one thing I'm sort of a bit curious about is actually the tail behavior of Gaussians and the extent to which this might give you overconfident or underconfident predictions somehow. It's you sort of think, oh, that will be mitigated because I'm because when I make my predictions, I pass everything through the logit or probit anyways, but it's not so obvious that that's a safe haven. And you might want to have more fine-grained control of the tails of these distributions. Another question you can ask is, is the difference of skill levels sufficient for prediction? So the way they do the logit and probit models is you look at the difference between the skill levels, you add some random Gaussian noise to it, and you threshold it. That's kind of one way of thinking of the probit model. And so there's reasonable questions of, is that actually a sensible difference? You kind of want something that encodes the monotonicity of skill levels, but is this the best way of going about it? And yeah, as I said before, is pure diffusion an appropriate representation of how skills drift over time? Do we want to shift it for something ergodic or something that's player dependent, and blah, blah, blah. And so from our perspective, what we're not interested so much is asserting that some of these are right and some of these are wrong. That's a hard question, and it's not our place at this stage. But a reasonable thing is we can ask whether they're true, and we can kind of test, does loosening this assumption make things better? Does adding a bit of flexibility to the model bias something more? And so building on that, we were trying to think what other model classes are tractable to work with and relatively flexible. And somehow the only thing that's anywhere near Gaussian models, I would say, is finite state space models. And so we kind of looked in this direction towards discrete models of skills. And so some of you will have seen some of Lorenzo's work in the past on inferencing factorial hidden Markov models, and that sort of feeds into what we're doing extremely nicely and was one of the motivations for the project. Okay, and yeah, we're sort of tentatively calling it discrete true skill because it's sort of built by perturbing the true skill algorithm of Microsoft, although I'm quietly not sure whether we can get away with that because it might be the case that true skill is copyrighted. And so that's something for us to figure out over time. But okay, since we're in the early stages, what we're going to do is build a discrete model that is, kind of mirrors the Gaussian situation nicely, check that everything still goes through safe, and then try to perturb it so we can gradually get more interesting dynamics or observation models and so on. So we're going to model the skill of each player as just taking a discrete value in an ordered set size m, and we don't expect that m will become huge, but nor should we expect it to be completely tiny. Maybe something in the range of 10 to 20 should give us enough fine graining. So sorry that my camera keeps dropping out. So instead of the Brownian motion for the dynamics, what we're using is a continuous random walk with reflection on this step. So basically, at unit rate, you either move up one or down one with sort of obvious modifications at the boundaries to make sure that you still have a uniform invariant measure. This is computationally convenient for reasons I can get into later. We're also looking at replacing this logit or probit type link function for the observation model by a general matrix, actually. So something that says when a player of skill level X and a player of skill level X prime play against one another, what is the probability that the first player wins, right? And so in a sense, it's like non-parametric. I mean, it's parametric. It's kind of, literally parametric because you have a matrix of size m squared, but somehow it's like, we're going to make it relatively unstructured aside from what I'm calling logical monotonicity. And by that, I mean the constraint that if you have a better player playing against a worse player, the probability of them winning goes up. Okay, it's just sort of a consistency constraint. And so on top of this, we're putting priors on the initial skill of each player. We're putting a hyperparameter for the skill of the continuous time random walk, so how quickly you sort of change your skill level, and we have to put some hyperparameters on these matrix entries. Yeah, and so the basic thing we're starting off with is actually, so I was complaining on the previous slides about whether a difference of skill levels is sufficient for prediction. Well, that corresponds to taking the matrix of win probabilities to be tuplets, which is to say constant along diagonals. And so that's sort of one simplifying thing we're starting with. But as I said, it's interesting to us to move beyond that relatively quickly. So with that model in mind, maybe I'll pause for a second to see if it makes sense to people, and I'll be fine for time. There's not huge amounts more to say.
Yeah, I think it's clear. Yeah, I think some people may need to drop out soon, but yeah, you can.
Cool. I'll run with it. So in terms of inference and computation, the engine for actually getting things done is the factorial hidden Markov model machinery of Lorenzo with Nick Whiteley, which is sort of published earlier this year. So a factorial hidden Markov model essentially is the structure we're describing, where you have the independent latent dynamics, and then you observe them through sort of sparse couplings. And so filtering takes place using what they call the graph filter. And the idea there is, again, throughout time, you have factorizing approximate posteriors for each of the player's skills. So you have a filtering distribution for player I, filtering distribution for player J. You take their product to get a predictive distribution for xi and xj. Then you have the observation for this match between them. That gives you a joint filter for these, and then you split it up again. Okay, so you take your marginal approximate filter for each player, fuse them into a product form thing, do Bayes' rule on that, and then split them up again. Okay, and the key thing is that because you have O of 1 players in each match, that this is very fast to compute. So that's what's called the graph filter. What's in the original paper is a bit more general because it sort of covers a slightly more general number of players somehow, but fundamentally the same thing is taking place. Smoothing takes place with the graph smoother, which is, as you'd expect, it's sort of the backward pass of the same algorithm, parameter estimation through EM. For most of what we're doing, it will be the sort of sufficient statistics type of EM, but we are sort of looking into ways of handling more general models where you need to do kind of a gradient descent on parameters. And one thing we're currently comparing a bit is whether these smoothing expectations that we're interested in, because they're always additive in time, whether we can use sort of forward smoothing techniques based on dynamic programming to save us a factor of 2. So there's sort of a particle filter version of this, but actually it's even easier for us because everything is deterministic. But the key thing is you can compute certain expectations forwards in time without having to do a smoothing path. And so it's a little bit cheeky here because since our filtering distributions are approximate anyways, it's not a priori obvious that the forward approximation of the smoothing distribution and the backward approximation will be compatible with one another. And so we basically want to test whether that's the case. And if it retains reasonable fidelity, then that makes a lot of sense for online estimation. Okay, so some complexity aspects I can sort of breeze over, but the key thing is, again, you want things scaling linearly in T and not too badly with M. So, standard hidden Markov models, they tend to have costs that scales quadratically with M, and so that's kind of a baseline. But because we have local dynamics and hopefully fairly sparse posteriors, there's reasons to believe we can keep it to linear or not too much more than that. If we move to more involved dynamics, we may have to consider more expensive routines in M, because you have to consider the transition dynamics of the latent state in continuous time, which without extra structure requires you to do matrix exponentials, basically, which can cost M cubed, more or less. Yeah, there's some sort of things you have to be a bit careful with the memory footprint if you're interested in doing smoothing, because you need to keep track of the forward filtering distributions. But we have some sort of ideas for sparsity for handling this. And so what we really need to do is sort of run this on some real examples and observe whether the filtering distributions are supported on, a dense subset of M or on a much sparser one. And somehow there's reasons why you should be able to adaptively thin things and not lose too much information. Okay, so I'll just wrap up here. So sorry for going slightly over. So the focus here is on probabilistic models for online skill ranking in competitive sports, like these examples I've given. What we're interested in contributing is this idea of moving from Gaussian latent skills to discrete ones, because we think that might offer a little bit of flexibility on the modeling side, and in particular also allow to probe these assumptions of, should we model the dynamics in this way, and so on. On the computational side, there's a lot of a lot of things we can do pretty fast in a generic way based on Lorenzo's methodology. And so we think this should be pretty robust to changing the model. And so what's to do for us is to sort of test on more simulated and real data. And really understanding these model assumptions is maybe the interesting applied thing for us, and to see whether these sparsity techniques are worth examining. Yeah, and then one thing we haven't talked about so much, because again, with the online nature, it's not completely clear, But here we've considered, filtering and parameter estimation, and it might also be interesting to do a Bayesian treatment of the parameters through something like, iterated batch import and sampling MCMC of different forms. Anyway, I'll wrap up there. Thanks very much for bearing with me.